Hello viewers, in today's class we are going to discuss one important application of derivatives related to proving of inequalities, right? So in this lecture we'll solve a very important inequality in calculus in which we have to show that log of x is always less than x minus 1 for all x greater than 1, right? So here we have to show that the logarithm of x is always less than x minus 1 for all values of x greater than 1, right? So here we can also rewrite this inequality as ln x is less than x minus 1, right? So here the notation log is for the natural log, right? So here the base is e. So let us start. Now, in order to prove inequalities of these kinds, what we usually do, we suppose or we assume an appropriate function, right? So let us assume an appropriate function, say y is equal to f of x, right? And f of x can be taken as the log of x minus x minus 1, right? Now see, we have to prove this inequality. So from the inequality itself, we can take help of assuming the function f of x, right? So if we take x minus 1 to this side, then we have log of x minus 1, right? So the first step towards proving these type of inequalities is to assume an appropriate function, right? So once we have assumed the function, let us apply the concept of derivative to the function. So let us differentiate both sides with respect to x. So let us find dy over dx, which is equal to f prime of x, and the derivative of log x is 1 over x, right? And here the derivative of x is 1 and the derivative of 1 is 0 because 1 is a constant. So we have 1 over x minus 1, that is 1 minus x over x, right? So the derivative of this function f of x is equal to 1 minus x over x, right? Now we'll use this derivative to show that this function f of x is a decreasing function when x is greater than 1. Now, from the concept of increasing and decreasing functions, we know that a function f of x is said to be a decreasing function if the derivative is less than 0, right? So this is the definition of decreasing function. So whenever the slope of a function or a curve is decreasing or it is less than 0, then we can say that the function is a decreasing function. So now let us look at the derivative. Now see, in f prime of x, we have the numerator as 1 minus x and the denominator as x, right? Now see, here we have the values of x which are greater than 1, right? So we have to prove this inequality for all values of x which are greater than 1, right? So whenever we have the values of x which are greater than 1, then they are all positive, right? Because all the numbers which lie towards the right of x is equal to 1 or greater than 1 are positive. So the denominator is always positive, right? Now let us look at the numerator. Now see, here we have 1 minus x. Now see, x is greater than 1. We are given x greater than 1. So whenever we have the numbers which are greater than 1, and when we find 1 minus x, then 1 minus x is always less than 0, right? For example, if we take, say, x is equal to 2, then 1 minus 2 is minus 1, which is less than 0. Similarly, if we take x is equal to say 5, then 1 minus 5 is less than 0, that is minus 4 is less than 0, right? So x greater than 1, then 1 minus x is always less than 0. So the numerator is always negative, right? So we can now here conclude that f prime of x should be less than 0. It means the derivative should be negative when x is greater than 1, right? So we have proved that this function f of x is a decreasing function for all x greater than 1, right? So this is the first statement which we have proved, that the function is a decreasing function for all values of x greater than 1. Now let us consider the graph of a decreasing function, right? So here we have the coordinate axis. Let us draw a rough diagram here. Suppose this is a decreasing function, right? This is y is equal to f of x, right? Okay, now let us take 2 points on this curve, right? So let us take this point as A and this point as B, right? And if we draw a line like this, and this point is say x1, this point is say x2, right? Now here we have the abscissa as x1 and x2, then the corresponding ordinates are f of x1 and this is f of x2, right? So the important thing about the graph of decreasing functions is that whenever we take any 2 points on the curve, that is x1 and x2, and here we can easily see that x1 is less than x2, right? So this number, that is this abscissa, is less than x2, right? But the ordinates, that is fx1 is greater than f of x2, right? So this is the important characteristic of decreasing function. So when x1 is less than x2, then f of x1 is greater than f of x2. So this property is utilized in most of the problems. So in this problem also we'll utilize this concept, right? So x1 is less than x2. So here we have x greater than 1, that is x greater than 1. So we can also write this inequality as 1, 1 less than x, right? So 1 can be treated as x1 and x can be treated as x2, right? And if we follow this definition, then we must have fx1 is greater than fx2, right? So f of x1 should be greater than f of x2 because here x1 is less than x2, right? So now fx1 is equal to f of 1, right? Because x1 is 1 and this is greater than f of x2. F of x2 is x, right? So x2 is x. Now we can find f of 1 from the definition of the function. So if we take x is equal to 1 here, then we can find f of 1 as log of 1 minus 1 minus 1. So log of 1 is 0. Here we have 0. So this is 0. So f of 1 is 0, right? And here we have f of x. So we have arrived at the result that f of x is less than 0, right? And f of x is log of x minus x minus 1 less than 0, right? And now if we take this term to this side, we have log of x less than x minus 1, and this is our desired inequality, right? So viewers, this is how, by making use of the concept of derivatives and the concept of increasing and decreasing functions, we can prove these kind of inequalities.